All right, you ready?
Sure.
Let me fluff out my hair. Okay. Okay, welcome back, everybody. Today we're doing, I think, my favorite topic in this entire course, and that's probability. So we're going to start off with sample spaces and probability. So probability is the chance that an event will occur. A probability experiment is a chance process that leads to well-defined results or outcomes. So think of this as like flipping a coin. Either your outcomes are heads or tails, or rolling a die, then your outcomes are either 1, 2, 3, 4, 5, and 6. Those are probability experiments. An outcome is the result of a single trial of a probability experiment, and a sample space is a collection of all possible outcomes for the probability experiments. Down here below, we have the different experiments: tossing a coin, rolling a die, answering a true or false question, or tossing 2 coins. And then the sample spaces are all the possible outcomes of each one of those. So tossing a coin, you can either have heads or tails. If you roll a die, you can have 1, 2, 3, 4, 5, or 6 showing on the die. True or false questions, it's either true or false, so there's only 2 outcomes. And then finally, if you toss 2 coins, there are 4 possible outcomes. You could have head, head, tail, tail, head, tail, or tail, head. Anything else there, Karen?
Nope, those are all like pretty simple sample spaces. So I think we're going to see now a couple examples where the sample spaces are a little bit more advanced.
Yeah, like example 1, you have here that we're going to roll 2 dice. And I think you said that the idea here is one way to calculate a sample space is just to write down all the possible outcomes and put them in a table, right? So do you want to talk about this slide?
Sure. So we're finding the sample space for rolling 2 dice. So it's basically up to you to kind of figure out like all of your possible outcomes or what can happen here. And just one way that your textbook kind of says that you can keep yourself organized is to use a table. So you can see how you can set up a table there. You have your die 1, die 2, and then you can kind of use like an ordered pair format to just keep track of all of your possible pairs. So like a 1 and a 1, a 1 and a 2, 1 and a 3, and so on. Now, the whole idea with finding a sample space is that you want to know how many outcomes are in the sample space. So by keeping yourself organized with a table there, you could count those up, and there's 6 on each side, so that's a total of 36 outcomes in that sample space.
Okay, perfect. Is that all you had to say for that slide?
Yep.
Okay. My daughter jumped in the room, so I muted myself for a second, but she's out now and we're good. So now another possibility of way to organize your thoughts when calculating the number of possible outcomes is to use a tree diagram to find the sample space. So here it says, use a tree diagram to find the sample space for the gender of the children in a family that has 3 children. So we're assuming here this is only binary outcomes. So either you have a boy or a girl. And so to build this tree, you basically have 2 outcomes: boy or girl for the first child, and then boy or girl for the second child, and then finally boy or girl for the third child. And so here we calculate that there are 8 possible outcomes. If you follow this tree, you could have girl, 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 boy, girl, boy, girl, or girl, boy, boy. Or if your first child is a boy, then if you go boy, girl, girl, boy, girl, boy, 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 girl, and boy, boy, boy. And so this tree is actually keeping track of the order of the children, not just how many of each you have there. So let's go through, yeah. So the first, I guess the outcomes, you make these great diagrams where it shows you, okay, one possible outcome is to go boy, boy, boy. And another one would be to follow that same leg for the first 2, but then have a girl at the end. So boy, boy, girl. And so I'm just going to click through the rest of these because I kind of talked through them already. But we see now that there are 8 possible outcomes in the sample space. And another way to keep track of this is basically at each step there were 2 possible outcomes, and we're going to have 3 children, so it's 2 to the 3rd different outcomes. So that's 2 times 2 times 2 gives you 8. Okay, Karen, you want to talk about this slide?
Sure. So just a couple more definitions. An event consists of a set of outcomes of a probability experiment. An event that has 1 outcome is called a simple event, and an event with 2 or more outcomes is called a compound event. So let's kind of look at an example of each here. So the event of getting a 6 when a die is rolled. So when you roll a die, how many ways are there to get a 6? Well, there's only one. You would actually have to roll a 6. So there's one outcome there. So we would call that a simple event. So let's compare that now with the event of getting an odd number when a die is rolled. So how many ways are there to get an odd number when you roll a die? Well, you could get a 1, you could get a 3, or you could get a 5. All of those would be odd numbers. So there's 3 outcomes in that event. So we would call that a compound event.
Right. Great. Okay. So classical probability, it's also sometimes called theoretical probability. It uses sample spaces to determine the numerical probability that an event will happen. In classical probability, we assume that all outcomes in a sample space are equally likely to occur. Okay, so we're highlighting those things. Again, this is also known as theoretical probability. So the probability of an event happening in classical probability is the number of outcomes in which this event occurs, so number of outcomes in E, divided by the total number of outcomes in the sample space. So then the probability, another way of writing that is just N of E over N of S, where S is the number of outcomes in the sample space. Karen, can you talk about this, the rounding rule? Because I think this is Connect Math specific.
Yeah, so, well, first of all, probabilities can be expressed as fractions, decimals, or percentages. The way that your textbook and Connect kind of works is they're going to always prefer fractions or decimals, and you just have to pay attention to like each specific question. It'll tell you, you know, whether to do it as a decimal or a reduced fraction. And there's really no consistency with it at all, so you just have to pay attention to the problem. Now, the actual rounding rule is obviously your fraction would have to be reduced, or if you're doing decimal places for probability, it's always 3 decimal places. Now, here's the exception. So let's say that you got a probability that was like 0.0000473. Okay, so Dr. Insco, oh, maybe he's can't hear me.
I can hear you.
Okay, I was going to ask you. So if you round 0.0000473 to 3 decimal places, what would that give you?
I mean, to 3 decimal places, then I have no idea because there's 4 zeros there. But I would just round up to the.
Well, yeah. So if you had to cut it off after 3 zeros, what would it be?
It would be 001. No, 000. I mean
000. Yeah. So you'd be essentially putting that your answer for probability was 0. Okay, right. And that's going to be a little misleading. You don't really want to say the probability of something is 0 if it's technically not 0. So the one exception to the rounding rule is that if it were to make you round to 0, instead of doing 3 decimal places, you're going to go out to the first non-zero place. So there you would go out to the 4, but then the 7 behind the 4 makes the 4 go up to a 5. So right. You would actually put 0.00005 in for that one.
Cool, thanks. Okay, so in example 3, we're asked to find the probability of getting a red face card, a jack, queen, or king, when randomly drawing a card from an ordinary deck. And just so you know what an ordinary standard deck of cards looks like, there are 52 cards. There's 13 hearts, 13 diamonds. So that makes 26 red cards. And there are 26 black cards. So there's 13 cards in each suit. So we have clubs, spades, diamonds, and hearts. And I think classical probability kind of came about because of card playing. People wanted to figure out probabilities of getting a certain hand. So this is like the standard example. But it's funny, I think fewer people play cards today, so maybe some of our students don't know how many cards are in a deck of cards and like how many are in each suit and how many are called face cards and so on. So we'll try to talk you through that in this lecture. But it says find the probability of getting a red face card. So here we're assuming red face cards are the jacks, the queens, or the kings when randomly drawing from a card of an ordinary deck. So when doing probability, you know, these problems they're fun, they're kind of tricky. It's like one of my favorite subjects because even after doing probability for years, I have to sit down and think about the problem and double check it to make sure I get it right. So that's just kind of warning to all of you that when you see Karen and I talking about these things, they're going to seem obvious when you see the answer. But when you have to do it yourself, you're going to have to really think about it and double check your work and maybe ask a colleague in the class, just because it's all about how you think about these problems to get these things right. And it just takes lots of practice. Okay, so again, red card, jack, queen, or king. Well, one way to do this is we could just say, okay, there are 3 hearts and there are 3 diamonds that are face cards. So that's 6 total out of 52. And so again, there are 6 total red face cards. That's the jack, queen, king of hearts and jack, queen, king of diamonds. And there are 52 cards total. So again, you take the number of things in your event divided by the number in the total sample space. The total sample space was 52 cards, and the red face cards are of those 6. So you get 6 over 52, or you can reduce that to 3 over 26. Karen, you want to talk about the second example?
Yeah, and I was just going to mention, like, the notation for probability, you're always going to use like a capital P, and then in the parentheses, you just put the name of the event. So like red face is just an easier way of saying, you know, a red face card. So anything like that where it's just obvious, you know, what it is that you're talking about, you would just put in the parentheses for your event name. Okay, so example 4 says that if a family has 3 children, find the probability that exactly 2 of the 3 children are girls. So we're looking for the probability of exactly 2 girls. Now, in order to answer this question, you have to know the entire sample space for 3 children. Okay, so that's why we did example 2, where we figured out the sample space for 3 children. So, do you remember how many total outcomes were in that?
8.
The one where we did the tree diagram. Yeah, there were 8. Okay, so if you're just, you know, doing this problem, you know, from the start right here, you would first have to figure that out. So you have to figure out the total number of outcomes in that sample space, and then you would go through and identify how many of them have exactly 2 girls. So if you look back at that tree diagram and the outcomes that we listed, count how many of them have exactly 2 girls. So that would not include the 3 girls. It has to just be 2 girls. And you'll see that there are 3 of them out of the total 8 outcomes. So
that would be girl, girl, boy, girl, boy, girl, and boy, girl, girl, right?
yes. Yep. So 3 out of 8 would be your final answer there.
Mm-hmm. Perfect. Thanks, Karen.
Mm-hmm.
Okay, this next slide, we're talking about what and or means. So this is in terms of probability. So this is one thing that you'll learn about mathematics is we use words that you use in everyday English, sometimes just slightly different because we have to pin down a specific meaning. So and in probability means that the events happen at the same time. So probability of getting a queen and a heart means that you're drawing the queen of hearts, okay? If you were to draw a heart, there would be 13 different options, but there's only one queen in that list of 13 options. Or means one or the other, or possibly both. So a lot of times in English, we say, I'm going to go do this or that. But in probability, saying I'm going to do this or that could mean that you're going to either do this or that, or both of those things. Okay, so the probability of getting a queen or a heart, I think maybe Karen highlighted these things. So the probability of getting the queen of hearts is 1 over 52 because there's only one queen of hearts in the deck of 52. But the probability of getting a queen or a heart is slightly different because there are 4 queens and there are 13 hearts. Okay. And then if we just added up everything in this column and everything in that row, we would get 17 possibilities, but one of those was counted twice. So that's why we're subtracting off this -1 because that's the queen of hearts was counted twice in that list, okay? So the probability of getting a queen or a heart would be 16 possibilities divided by the 52. So that gives you 4/13. Okay, so again, probability of queen or hearts is 4/13 or 16 over 52 because of all the different possibilities. There were 13 in this row and 4 in this column, and one of those is shared. So we had to subtract that one off because we counted it twice if we just added them up. Is that good, Karen?
Yep, so you just have to be careful whenever you're doing a probability that has the word or in it. You have to be careful if there's overlap.
Right.
So if you ended up, double counting anything, you do have to account for that and basically subtract off that overlapping part.
Great. Okay. So, Karen, you want to do this next one? Probability of getting a queen or a king?
Yeah, probability of getting a queen or a king. So you would just ask yourself, all right, how many queens are there? There's 4. How many kings are there? There's 4. Did I double count any? Is there a way of picking a single card and having it be both a queen and a king? Well, no, so I don't have to worry about overlap in this part. So I would just simply add the 2 4s, and that's going to give me 8 possibilities. So the probability of that event would be 8 out of 52 or 2 out of 13. So or doesn't necessarily always imply that there's going to be overlap. It just simply depends on the situation, and it's basically up to you to figure that out within each problem.
Yeah, so those are like non-overlapping events, or sometimes we call those independent events, right?
Mutually exclusive.
Mutually exclusive. Yeah. Okay.
We'll get there.
Yeah. Okay, so the probability of an event is a number, either a fraction or a decimal, between 0 and 1, and it's usually denoted by a P of E, okay? Less than or equal to 0 and 1. The sum of the probabilities of all the outcomes in a sample space is always 1. And if in an event E cannot occur, then the probability is 0, okay? And if an event is certain, then the probability is 1. And so I think this is one of the reasons why it's important to note that when we rounded, in the previous example, when it was 0.0000473, it was important that we didn't write that the probability was 0, because that would mean that the event was impossible, but there was a very small possibility that could happen. It was about 0.00005, right?
Yes, exactly.
So it's extremely
Yeah.
unlikely, but it's not impossible.
I was just going to say, out of those 4 rules, probably the most important one is number 1. You just want to keep in mind that probability should always be a number between 0 and 1. So a lot of times, students will give me answers where they're saying that the probability of something is either over 1 or over 100% or somehow a negative number. All of those types of answers should be like huge red flags that you did the problem wrong. So don't even, be tempted to put that into the computer. You should catch yourself and be like, okay, obviously the probability can't be 20 point something.
Right.
So let me go back and, reevaluate my work. So just keep that in mind. Probability always has to be a number between 0 and 1.
Mm-hmm. And it should never be negative.
Yeah.
Okay. So the complement of an event is the set of outcomes in the sample space that are that are not included in the outcomes of the event. The complement of E is denoted E bar, and we should say that sometimes other books use E to the C or E prime to denote the complement. Are there any other notations you commonly see?
There's E bar, E C, E prime, or not C. Those are the main ones. I think I listed them there. Yeah.
Okay, yeah, not E. Perfect. Okay, so examples would be like selecting a month that has 31 days. The complement of that event is selecting a month that does not have 31 days. Rolling 2 dice and getting a sum that is an odd number. So if the complement of odd is even, so you'd say the rolling 2 dice and getting a sum that is an even number is the complement of that event.
Yeah, and technically, like, you could put that the complement is rolling 2 dice and getting a sum that is not an odd number.
Yeah.
That would be an acceptable answer. But a lot of times with, probability stuff, you do want to try to put it in terms that it's going to help you out the most. So in that case, instead of saying not an odd number, it might be better to say that it's an even number.
Yeah. Okay. So there's a rule for calculating complements, and it's written in 3 different equivalent ways. So the probability of not E is the same as 1 minus the probability of E, because 1 is the probability of the entire sample space, and you're just subtracting off the probability of E to get the probability of the complement. You could also write that as P of E is 1 minus P of E bar, or you could write P of E plus P of E bar is equal to 1. So this is a very useful rule because a lot of times it's easier to calculate the probability of an event than it is to calculate the probability of its complement, and vice versa. So let's take look at an example of example 5. It says In a study, it was found that 23% of the people surveyed said vanilla was their favorite flavor of ice cream. If a person is selected at random, find the probability that the person's favorite ice cream is not vanilla. So this is just asking you to apply this rule. So can you guys all figure out what the probability of finding someone that is not vanilla for their favorite ice cream? Well, that would be 1 minus the probability of vanilla, which is 1 minus 0.23. So you should get 77%, or 0.77 is the probability of their favorite ice cream not being vanilla.
Yeah, and as far as your answers, the one time your textbook is going to want answers as percents is when percents were given to you in the problem. So that's why on this one, because it gave us the statistic as 23%, we'll put our final answer back into a percent.
Cool. Can you tell us about empirical probability?
Yeah, so empirical probability relies on actual experience to determine the likelihood of outcomes. So it's based on observation. So this is going to be where we actually have like some sort of data or a frequency distribution, and we're going to use that information to calculate probability. And empirical probability is also called relative probability. So you might hear us kind of use those terms interchangeably, or if you Google stuff or get help from someone, just know that both those terms do mean the same thing. As far as the formula, I'll just read the box really fast. The probability of a given event or of an event is just going to be the frequency for that class divided by the total frequency. So it's still the same kind of basic idea of classical probability. But let's do some examples here. So example 6 says that a sample of 50 people has the frequency distribution shown. Find the probability that a person has type AB blood. Okay, so we want the probability of AB. So that's going to be the frequency for the class of AB divided by the total frequency. So over in your table, the frequency for AB is 2. So 2 will be in the numerator. And then total, well, I guess we do know it says a sample of 50 people, but if it didn't say that, then you would add up your frequency column. So 22 plus 5 plus 2 plus 21 is 50, so that's 2 over 50, which reduces to 1 over 25.
Perfect, okay. And so the next one says, what's the probability of having type A or type B blood? So now what we want to do is we want to look at the type A row and say, okay, that's a frequency of 22. And then the or is plus 5. And then it's impossible to have type A it's impossible to have type A blood and type B blood at the same time. So we just add those together and you get 27 over 50 for the probability of having type A or B.
So then C says the probability of neither type A nor type O. So another way of thinking about that, if it's not A or O, then that means you either have B or AB. Okay, so you can kind of translate it like that for yourself. So then the probability of type B blood is 5, and then, or frequency is 5, AB was 2, so we'll add the 5 and the 2, so we get 7 out of the total of 50.
Perfect, okay. Does not have type A blood. So if you don't have, does not have type AB blood. So if you don't have type AB blood, then you either have A, B, or O. So we're just going to add up the frequency for those. So A is 22. Oh, this is using the complement rule. You could do what I just said. You could add up 22 plus 5 plus 21, but it might be faster just to subtract off the probability of having AB blood, which there's 2 over 50. So then you would end up with 48 over 50 or 24 over 25. So this is an example where using the complement is a faster calculation because you only have to calculate one probability and then take the difference, 1 minus that.
Yeah, so I was just gonna say, like, so your instinct was to just add the other 3. And that certainly works when you only have 3 other ones to add. But if you have a giant table, then it's probably faster to just use the complement instead of trying to add up all of the other frequencies. But either way is acceptable, either way is right, and you should get the same answer either way.
Yeah. Okay. So that's what I love about this section is we have so many interesting examples and just lots and lots of practice problems. So example 7, can you hear that?
Yeah, someone's not happy, I
I
think.
think she's just really excited actually.
Oh, okay.
This is a normal occurrence in our house, right? Okay, so example 7, a hospital records indicate that knee replacement patients stayed in the hospital for the number of days shown in this distribution. Find the following probabilities. So find the probability that a patient stayed exactly 5 days. Karen, I'm gonna let you take over until she
Okay,
quiets down.
no problem. So probability of exactly 5 days. So that's easy, exactly 5. Just get the frequency for 5, which is 56. I don't think they gave us the total here, so you have no choice but to add up all of those frequencies, which gives you 127. So your final answer is 56 over 127. Part B says a patient stayed fewer than 6 days. So let's just think about what that means. So fewer than 6, then we should be considering the results of 3, 4, and 5. Okay, so we'll just add up the frequencies for 3, 4, and 5. So 15, 32, and 56. Put that all over the total of 127. And that'll give us 103 over 127. Part C says a patient stayed at most 4 days. Okay, so think about what at most 4 means. So that means up to 4 and including 4. So 3 or 4. So we'll add the frequencies for 3 and 4, so 15 and 32, put that over 127, so we get 47 over 127.
Okay.
And then one more here, so a patient stayed at least 5 days. So at least means 5 or more, and we do want to include the 5, so 5, 6, or 7. So we'll add the 56, the 19, and the 5, put that all over 127. So we get 80 over 127. So kind of the whole point of this example was just to show you that you do need to pay attention to the words as well. So exactly 5, fewer than 6, at most 4, at least 5. So just make sure that you're reading the questions carefully and kind of paying attention to the actual words in there.
Perfect. Okay, so the law of large numbers. So the law of large numbers says that when a probability experiment is repeated a large number of times, the relative frequency probability of an outcome will approach that of its theoretical probability. So like in a good example of this is if you flip a coin, you would expect to get heads 50% of the time. That's the theoretical probability. But I think anyone that was ever like a captain on a sports team or something knows that if you flip a head 10 times, you're not necessarily guaranteed to get 5 heads and 5 tails. You might get 6 or 7 heads in a row, and so if you do 10 tosses, you might get 8 heads, and so that's 8, 10, or 80% of the time, just in that experiment of tossing it 10 times. But if you toss it 100 times, it's going to tend towards getting closer to 50-50. So if you did 100 tosses, you might expect to get 67 heads, or so you'd have 67% frequency. And then if you did this, 10,000 times, pretty soon you're going to get very close to 50% heads, 50% tails. I would have guessed that this would be even closer to 50% than 54%. I'm kind of skeptical that maybe this coin is unfair at this point. It's just mildly biased towards heads.
Okay, so students always ask me, where did I come up with these numbers? And I literally just made them up. So I did not actually toss a coin myself that number of times. I just kind of made up random numbers just to show you the idea that the more you toss the coin, hopefully the closer you're getting to 50%.
Gotcha. Yeah, I would guess.
But you're right. That might signal to you that it's unfair.
Close to 50%.
Yeah.
But you guys, the students should go home and do an experiment for themselves. That's a probability experiment. Just flip the coin 100 times and see what you get. Okay, so then subjective probability. So subjective probability uses probability value based on an educated guess or estimate, employing opinions and inexact information. I think a good example of this is when people say, well, we have a 50% chance of rain tomorrow in Florida, in Fort Myers, because it's July and it basically rains almost half the time. Or maybe they know that under these situations, typically half the state is covered with clouds at that given time, so it's probably going to rain on you. But I just love it's like being a weatherman in Florida. It's like you give these probabilities, and it's like, well, where did that come from? Kind of an example, right? Okay.
Yeah, the subjective probability, that's the probability that we actually encounter like all throughout our everyday lives, you know, whether it's listening to the weather in the morning or, you know, throwing the sports channel on and hearing something, or you go to your doctor and they give you some sort of, you know, probability statistic. You know, it's just good to keep in mind that they're all, you know, they're educated, but they are educated guesses or estimates.
Right. Yeah. Especially with the doctors, right? Okay. So now we're gonna. This is a shorter section, so we'll just keep moving right along. So this is the addition rules for probability. So two events are mutually exclusive events or disjoint events if they cannot occur at the same time. They have no outcomes in common. So I think I talked about this a little bit earlier. Mutually exclusive means you have two different events and there's no overlap, right? I think I called them, what did I say before, disjoint or
You said independent.
independent? Oh yeah, independence when you have two events that happen and they have nothing, one does not affect the other. Sorry,
Right.
I
Yeah.
misspoke. Okay. I meant to say disjoint or mutually exclusive. So when two events A and B are mutually exclusive, the probability of A or B will occur is always probability of A plus probability of B. And I think Karen wrote this down just to let you know that in Connect Math, they use the symbol union for or, okay? And that's common notation. It's basically you either write A or B or you write A union B, and those are supposed to mean the same things. It's just a little frustrating that the book and Connect Math couldn't use the same notation when this Connect Math program was written for this book. Also, and is going to be the N sign or like an upside down cap. We'll see that in a little bit, I guess. Okay, so for three mutually exclusive events, A, B, and C, the probability of A or B or C is going to be the probability of A plus the probability of B plus the probability of C. So that's just applying this rule twice, basically.
Yeah, so it extends to any number of events. You know, you could have 100 events. As long as they're all mutually exclusive, then you just add up all of their individual probabilities.
Mm-hmm. So in example 8, it says the city has 9 coffee shops, 4 Starbucks, 3 Dunkin' Donuts, and 2 Caribou Coffees. If a person selects one shop at random to buy a cup of coffee from, find the probability that it is either Starbucks or Dunkin' Donuts. So obviously Starbucks and Dunkin' Donuts are disjoint events because I don't think there's ever been a Dunkin' Donuts inside of a Starbucks. And so there you just take the 4 ninths plus the 3 ninths and you get 7 ninths. Okay, you want to talk about this one? Not mutually exclusive?
Yeah, so not mutually exclusive is obviously where there is going to be some sort of overlap between the outcomes of your two events. And your formula for that, it's still the probability of A or B. So you're still going to add the probability of A plus the probability of B. But now you want to make sure that you subtract off that overlap. So however many outcomes occur from them both happening at the same time. So you subtract the probability of A and B. And we actually already did that already back when we did like the probability of, I think it was like getting a queen and a heart. Mm-hmm. You know, we just intuitively did that. We counted the queens, we counted the hearts, and then we said, all right, how many did we double count? And we subtracted that off. Mm-hmm. So we were doing this formula just before we even really knew what the formula was. And like Dr. Insco said, you just want to be aware that on Connect, your notation might change up a little bit. So or is the same thing as the union symbol, and then and is the same thing as that intersection symbol. So either way, they mean the same thing. And then for three events that are not mutually exclusive, you can see that the formula immediately gets pretty complicated. So let's just kind of look at it here. So for three events, you still add each individual event, the probability of each one. Then you subtract each pairwise probability. So you pair together A and B, subtract those, A and C, B and C. But then at the end, what you actually have to do is add back the probability that all three events happen at the same time. So this is kind of a fun formula to apply. It's not as scary as it looks. We're going to do a couple practice problems and you'll see us apply the formula when we get to there. But example 9 says that a card is drawn at random from a deck of cards. Find the probability that it's either an ace or a black card. Okay, so we want the probability of ace or black.
Mhm.
So before you even like decide whether or not they're mutually exclusive, no matter what, you're gonna have to find the probability of getting an ace and then add that to the probability of getting a black card.
Mhm.
Now, Dr. Insco, let me ask you, if you pick a card, oh no, wait, probability of black, yeah, if you pick a card, is there a way that it's both an ace and a black
Yeah, that can happen
card?
different ways.
Yeah, so they're not mutually exclusive. So we do want to subtract the probability that the card is both an ace and a black card. If you just want to click
Yep.
for me, that'll pop up there.
Okay.
Okay, cool. So the probability of getting an ace. So let's see, there are 4 aces out of the total 52. Half of the deck is black, so there's 26 black cards. And then which ones did we double count? Well, there were 2 aces that are black cards. Okay, so those got double counted, so that's our overlap. So we want to subtract the 2 black aces, and then we'll add up all those fractions, and we get 28 out of 52, or 7 out of 13.
So in Connect Math, do they need to reduce it down to 7/13?
Yes, they absolutely have to put a reduced fraction or they get it wrong. And then they just have to pay attention to the directions as far as whether they specifically want a decimal or a fraction.
Okay.
In class, I like fractions.
Yeah.
So all of my answers are usually fractions on here, but they just have to pay attention and connect.
Okay. So in example 10, it says in a hospital unit, there are 8 nurses and 5 doctors. Of those, 7 nurses and 3 doctors are female. If a staff person is selected, find the probability that the subject is a nurse or a male. And so this is a good example where it's a great idea to make a table because there's a lot of information going on in those sentences. And if you were just to try to calculate that in your head, it'd be very easy to get confused or mixed up. In fact, I'm already confused and mixed up just reading it one time. So I might read the sentence again, and then I'm gonna try and put that into a table. So there are 8 nurses and 5 doctors total, right? So that's an 8 and a 5 there. And if we look at the next sentence, it says 7 of the nurses and 3 of the doctors are female. So we have 3 female doctors, we have 7 female nurses. And so then if you do some math, I guess you see that there's going to be 1 male nurse and there's going to be 2 male doctors. Okay, so then total we have 10 females and we have 3 males. And there are 13 individuals altogether. So that's just putting all that information to a table. And then what were we asked to find again? It says if a staff person is selected, find the probability that the subject is a nurse or a male. Well, okay, so the probability of being a nurse is 8/13. The probability of being a male is 3/13. But then we have to subtract off the probability of being a nurse and a male. Okay, well, how many are nurses and males? 1. So you have to subtract off 1/13. So we end up calculating the probability of selecting a nurse or a male is exactly 10/13. Is that good, Karen? Is there anything I should add?
Yeah, no, that was good.
Okay, so I'll let you go over some of the extra practice problems then.
Okay, so the first one, which of these cannot be considered a probability outcome? Okay, so again, you don't want numbers that are negative or larger than 1, or if it's a percent, it shouldn't be larger than 100. So B is definitely out because that number is larger than 1. Let's see, E is negative, so that's not good. F, 125%, doesn't make sense when you're talking about probability, so that's out. And G is negative, so that's out. And the others all look good to me. So the others would be acceptable probability answers. Let's see, number 2 says that of all the murder victims in 2010 whose relation to the offender was known, 24.8% were killed by a family member and 53% by an acquaintance. The rest were killed by a stranger. What is the probability that a randomly selected murder victim was killed by a stranger? Okay, so one way we can do this if we want to figure out the probability that the person was killed by a stranger is to use the complement rule. Mm-hmm. So we know that the total percent has to be 100. So if we subtract off the percent that were killed by a family member and subtract off the percent that were killed by the acquaintance, that'll give us what's left over, which was the percent killed by a stranger. So you just have to do 100% minus the 24.8% minus the 53%, and that gives you 22.2%.
And I guess that we're assuming that the family members and acquaintances are disjoint.
Yeah.
Okay, I need to move our heads because they're blocking the top of this question now. So it says, if one card is drawn from a deck, find the probability of getting these results. Express the answers as reduced fractions. So the probability of getting an ace, well, there are 4 aces, and there are 52 cards in the standard deck, so that's 4 over 52, or 1 over 13. So B says a 6 and a spade. You want to tell us about that, Karen?
So, okay, you have to pay attention to the words and or. So, and means at the same time. So, in other words, you pick a card and it's both a 6 and a spade in that one card. So, how many ways are there for that to happen? Well, there's only one, the 6 of spades.
Mm-hmm.
So, that would just be 1 out of 52.
Right. So that's interesting. What if it's at a spade and a 6, right? Like, could you use the disjoint formula or no? You just have to like translate that and say that's definitely the 6 of spades, and there's only one of those.
If it just switched the order that it wrote it?
Yeah, I don't know. Like, I mean, there's 4 6s, right? But only one of them is a spade.
Yeah.
I guess like you could say there's 13 spades, but only one of them is a 6. And so I guess it's
Yes. Same answer.
Okay. And then, so the next one is a red king. So there isn't an and, but it is saying it needs to be red and it needs to be a king. Well, there are 2 red kings because there's the king of diamonds and the king of hearts, right?
Yep.
So I think we get 2 over 52 or 1 over 26.
Okay, D says a red card or a black card. So let's see, there's 26 red cards. There's 26 black cards. You don't have to worry about overlap because the card is either red or black. So you get 52 out of 52, which equals 1. And hopefully that makes sense. So a probability of 1 is the same thing as 100%. So if you pick a card out of a deck, what's the probability that it's either going to be red or black? Well, obviously those are your only choices. So it's 100%.
Right. Okay, so E, it says a red card or a 7. So how many red cards are there? There are 26 red cards. And there are 4 7s, but there's some overlap there, right? 2 of those 7s are red. So what we want to do is we want to add up the 26 plus the 4, but we need to subtract the overlaps. That's 30 minus 2 gives you 28 over 52, or 7 over 13 for the probability of picking a red or a 7.
Yeah, so then F says a red card and a 7. Okay, so you pick one card and it has to be both red and 7. Well, there are 2 cards that are both red and 7, so that's 2 out of 52 or 1 out of 26.
Mm-hmm. And then a diamond or a heart, well, that's essentially the same as a red card, right? There are 26 red cards. Or you can look at this as there are 13 diamonds and there are 13 hearts. So you add those together and you get 26 over 52, or 1/2 for the probability of picking a diamond or a heart.
Yeah, and then a diamond and a heart. Well, can you pick a card and it be both a diamond and a heart?
No.
No, that's impossible. So there's 0 cards that would make that happen. So that's 0 out of 52 or just 0.
Cool. Okay, example 4. If one card is drawn from an ordinary deck of cards, find the probability of getting the following: a king or a queen or a diamond. So
this is that longer formula where it's 3 mutually exclusive or non-mutually exclusive events.
Mm-hmm. Yeah, so we want to calculate the probability of a king, probability of a queen, probability of a diamond. So king is 4 out of 52, queen is 4 out of 52, diamond is 13 over 52, and then minus the probability of a king and a queen. Well, that's 0 because you can't be a king and a queen at the same time in a deck of cards. A king or a diamond, that can happen, right? So that's a 1 out of 52 chance of being a king and a diamond.
Mm-hmm.
And then queen and a diamond, that could happen. That would be a 1 out of 52. And then finally, king and queen and diamond, that's 0 because you can't be the king and the queen. So I've just written these down again. So this is 4 out of 52 for the probability of being a king, 4 out of 52 probability of a queen, 13 over 52 for probability of a diamond, minus 0 for the king and queen, minus 1 for the king and diamond, and minus 1 for the queen and diamond, and then finally plus 0. So when you tally all that up, you should get 19 over 52, which I don't think you can reduce any further because 19 is a prime number. Okay, I'll let you do B, Karen.
So B is a 7 or a diamond or a red card. So I didn't bother writing the formula out for this one. I get lazy too, like students sometimes. So let's see, but let's do each one individually. So the probability of a 7, there's 4 7s, so 4 out of 52. Diamonds, there's 13, so 13 out of 52. Red cards, that's 26, so 26 out of 52. Now you just want to pair together each of them and subtract that off. So 7 and diamond would be the 7 of diamonds, so there's 1. A 7 and a red card, there's 2 of those, so we'll subtract 2 out of 52. And then a diamond and a red card, well, all of the diamonds are red, so you'll subtract 13 out of 52. And then you want to add back the probability of all of them happening at the same time. So is there a card that is a 7, a diamond, and a red?
Yes, there's
yes.
one.
Yeah, there's one of them. So we want to add the 1 out of 52 back and tally all that up, and you get 28 out of 52 or 7 out of 13.
Yeah, and like if you were like following along with that calculation, you would realize it's like, okay, so we calculated the probability of 7 or a diamond or red card first, and then we subtracted off the 7 of diamonds, and in the very next step, we subtracted off the 2 red 7s. Well, that means that you subtracted off the 7 of diamonds twice, and so that's why in the very last step, we will go back through and add in the intersection of all 3 categories, which happen to be that 1 7 of diamonds. So if like you can kind of see this as like you're putting the cards down, and then you said, okay, if you have a 7 of diamonds, hand that back to me. But you basically said it twice, right? So that's why you wanted to add that 1 back in. I don't know if I cleared anything up for people.
No, that was a good explanation. That made sense.
Okay, cool. Okay, another example. This is one we're going to fill out a table. So it says in a statistics class, there are 18 juniors and 10 seniors. 6 of the seniors are females and 12 of the juniors are males. If a student is selected at random, find the probability of selecting the following: a junior and a female. So this is where you wanna make a table, and unfortunately I clicked too far and it filled in the table already, but we had 18 juniors and 10 seniors. 6 of the seniors are females, so that's where we got the 6 here. 12 of the juniors are males, so we put a 12 there, and then we had to do the math to get a 6 junior females and 4 senior males. That gives us the totals of 18 and 10. And then we have to calculate by adding up this way to get the 12 and the 16. And then finally we see 12 plus 16 is 28. So we have 28 total students. So then the question was, what's the probability of selecting a junior and a female? Well, junior and a female means you have to be in this box right here. So that's 6 over 28, because we have 28 total. And so that's 3 over 14. Karen, you want to do junior or a female?
Yep, so junior or a female. So or means you add up each of them individually and then you subtract any overlap. So that's going to be the probability of a junior plus the probability of a female minus the probability of the person being both junior and female. So let's see, for junior, the total for juniors is 18, so that's 18 out of 28. The total for females is 12, so that's 12 out of the 28. And then the J and F is where they overlap. So that's where they actually like cross each other in the table. So that's the 6. So we'll subtract 6 out of 28, and that comes out to 24 over 28, which reduces to 6 over 7.
Mm-hmm. Okay, and then junior or a senior, where it's like intuitively everyone in the study was either a junior or senior. So that should be 1, but we can also do the calculation. So the probability of being a junior is 18 over 28, and the probability of being a senior is 10 over 28, so you get 28 over 28, which then reduces to 1. So we're certain in this study to either pick a junior or senior because that's the entire sample space. Karen, you want to talk about this one?
Yep, so it says a postal carrier distributes first-class letters, advertisements, and magazines. We have that data there about what she delivered. If an item of mail is selected at random, find these probabilities. So the first thing I would do, if your table or the data they give you doesn't have the totals done for you, then I would do that first. So you just add up all your columns, add up all your rows, and make sure you get the totals for each of those. So I went ahead and did that over there. Okay, so let's see. Part A says the item went to a home. Okay, so that's just going to be the total for the home row, which is the 934, over the total for the entire table, which is the number in the corner there, the 2784. So 934 over 2784 reduces to 467 over 1392. And I just wanted to tell you guys, in your calculator, if you like type 934 divided by 2784, press enter, it's going to give you a decimal, okay? If Connect Math wants it as a reduced fraction, all you have to do is press math, enter, enter, and it puts it back into a fraction and it reduces it for you. So just remember, math, enter, enter, and your calculator will give you the reduced fraction answer.
Cool. Okay, so problem item B says the item was an ad or it went to a business. Okay, so now we have to do the probability of ad or business, which is going to be P of A plus B of B minus the intersection, right? So probability that's an ad, well, that would be that'd be 1,427. And then probability that it goes to a business is 1,850. And then we need to subtract off the intersection, which the ads that went to businesses was 1,021. So hopefully I did all that right. And so then we get 47 over 58 when you tally all that up. I think you skipped a step in the calculation there, Karen. But
oh, yeah, I just put the reduced answer for sure.
Yeah, okay.
Okay, and then part C says the item was a magazine that went to a home. Okay, so that's another way of saying that it's, well, magazine and home, basically. So magazine and home, you just want the overlap of the magazine column and the home row. So that's 203 out of the total for the table. And then that reduces to 7 out of 96.
Cool. And I think we're done for this video. We're going to pick up here in the next video. Great, thanks.